Greetings, everyone. I'm going to go through here the steps for completing the Brownian Motion 3 lab. So first, a note. I'm going to do the first few steps. I think there are 9 total, so I'm going to do 1 through 7 for you, so it's not few really. I'm going to go through them in some detail because I want you to know how I did them. You are welcome to redo them. If you want to, you will need to download the tracking software I'm going to show you, and then manipulate it as I show you. You will need to know the details of how I did what I'm doing in order to take your practicum in a couple weeks. And at the end, there will be an Excel file on Sakai, and you will need to complete steps 8 and 9 on your own. So first off, step 1, you have to get the video tracking software. It is available at this this website. It's called Tracker. If we were in the lab doing this, we would use Logger Pro, but I don't have Logger Pro on my computer. Tracker is free to download. Okay, so step 2, you need to get the files from Sakai. Before I left, I put up onto Sakai 3 MP4 files and 1 JPEG. They're all in a folder in the resources folder called Brownian Motion 3. Guys, I didn't get through looking at your videos, so I just chose 3 of mine. We're going to work with Dr. M1 today. Okay, so the first thing you need to do is you need to open up Tracker. And then pull into it. Oh, maybe. I guess this is as good as it's going to get. Hold on. I'm going to fuss with the window for just a second. Okay, now we can see the whole thing. Pull into it the JPEG that you just got from Sakai. It's a really exciting picture here. This picture was taken of a micrometer through the microscope on the exact same settings that you used when taking the videos and what I used when taking my video. The distance between each line is 10 microns. So what we want to do is use this to set up a coordinate system. Okay. So to do that, we are going to, put in a calibration stick. Now to do that, we click and then we click down here. Notice outside of line to outside of line. And then we tell it how big this is. It is not 523.6 meters. Each spacing is 10 microns. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spacings. Hold on. Sorry, my computer did something funny there. So this would be 10 e to the negative 6 meters. Okay. Now that's very nice, but we don't have that distance or that scale easily on the videos that we made. What we have is the diagonal distance. So now what we're going to do is we're going to make a measurement to figure out what that diagonal distance is. And I have to remember how to make a measurement now. New measuring tools. There we go. New tape measure. So we are going to take this guy and move this out of the way. Okay, so there's one end corner to corner, down here for the other one, something like that. It should be about 1.5 times 10 to the minus 5 meters, and we are right in that ballpark. Write down this number. You're going to need it. Well, I'm going to need it for the next step, so I'm going to write it down. 1.498 times 10 to the minus 5 meters. Okay, we are done with this at this point. So the next thing we're going to do is open up a new tab. The reason I'm not getting rid of it is just in case I have to go back to it. And in that new tab, I'm going to import the video. So here it is. So the first thing we need to do here is set our distance. And to do that, we're going to do new calibration stick, and we're going to go from corner to corner and use that number that we just got. So 1.498 e negative 5. Okay, that's done. Okay. At this point, we are ready to start tracking the motion of these particles. So basically, we're going to get a data file which will give us the x and y positions of the particles. I really wish that it didn't have that little window that keeps popping up had a "don't show this again" message. Okay, so for that, we're going to create a new point mass. So there it is. You can tell it's going to give us time, which we don't really care about, x position and y position. And at this point, we just need to choose a particle and start tracking it. To do this, you hold down Shift and start clicking. And click on it for as long as you can follow it and see it. Oh, looks like I lost it. When you lose it, pick a new particle, but don't pick a new particle right next to where you picked the old one. Make a large jump, and then we can remove later the large jumps from the data fairly easily. So I'm going to go down here and track this one for a little bit. And we need to do this for all frames of the video. Oh, looks like I lost that one. So I'm going to go up here. Let's try this one, shall we? Okay. So you can see it tells us where we clicked, the little clusters, things like that. And it made this chart. Now, for the sake of expediency, you guys really don't need to watch me click on all of these for 244 frames. We're going to pretend that I am done with it. At that point, you come up to File, Export, Data File. That pulls up this window. You tell it, I want to export all the cells. My delimiter I want is a comma because you want a CSV file. You want full precision. You hit Save As. It pulls up this window. So I'm going to save it as Dr. M1 Brownian Motion 3 data. And then I'm going to put 2 under it because this is the second time I've done this. And then make sure you give it the CSV file extension, otherwise you won't be able to open it. And you hit Save. And that created that file for us. You can close this. I'm going to minimize this and come back to here. Okay, so we did step 3 and determined our calibration distance. We've also, at this point, completed step 4, where we set the scale on the video. And we completed step 5, where we track the spheres. And we've completed step 6, where we exported the data as a CSV. The next part of step 6 is to open this CSV file in Excel. So here is our CSV file in Excel. Isn't it exciting? The next part of that step was to do a Save As and save it not as a CSV, but save it as an Excel workbook. Click Save. Okay, the reason for that is some of the manipulations we're going to do won't resave if you keep it as a CSV. Now, this data file only has 33 frames in it. We need the full video. So I'm going to open the other CSV file that I made. Oh, hold on. I'm going to close that and then reopen it. I have no idea what I just did, in all honesty. Okay. Take 2. Opening my other CSV file. It looks like this. Very similar to what we just had, but you can see that it has all 244-ish entries. A couple more, actually. Okay. Oh, I forgot to save as. So File, Save As, save it on the current folder. And as I've already done this once, I'm going to make this number 2. And actually, this would be, we're going to save it under 1B. That works for me. Okay, so that lands us here. Now we're going to go back to PowerPoint. In PowerPoint, we are told at the end of step 6, save it as an Excel workbook. We did that. Now step 7, we want to calculate the changes in position. The nice thing about Logger Pro is it would do this for you. We, however, don't have Logger Pro, and it wasn't easy to do in Tracker. So it is fairly easy to do in Excel, just a little tedious. Okay, so we want to calculate the change in position for X and Y. So what I'm going to do is I'm going to take and make an equation. dx is going to be this one minus that one, and that will tell me how much it moved between that step. dy is going to be the same thing. It'll be this one minus this one. And now you can grab those two and drag them down. You want to stop one below the bottom because the bottom one isn't going to have anything to subtract from it. Okay, so we made dx and dy. Our units were meters, so I've added units to the spreadsheet at this point. What is next? Calculate dx and dy in new columns and then create a big dx column. And this is where we're going to take the dx information and the dy information and put them one below the other, just as we did in Brownian Motion 1, based on the assumption that our motions are independent of each other. So make a new column. We're going to call this just big dx. Again, units of meters. There was a note on the PowerPoint that you need to make sure you copy the values and not the formulas, because if you copy the formulas, things will not work correct. Oh, I'm screwing it up. Okay, hold on. Sorry, I started inputting a formula for some reason. I don't know why it does that. We'll do it this way. So I'm going to grab this, copy it with a Control-C, paste it with a Control-V, and I see down here there's this thing that allows me to paste only the values. And now I'm going to copy the dy column. Again, a Control-C, paste it with a Control-V, and again, I want to make sure that I paste the values. Okay, what is our next step? Our next step, we've completed 7. Okay. Okay, so we completed, apparently I can't count. We have 2 step 7, so I'm going to keep going with step 7 here. We need to create a histogram. So as a reminder for the histogram, I gave this little example here where I can take student grades on an exam, and I can look at how many students got A's, and how many students got B's, and how many students got C's, right? And I can make a graph where the horizontal axis is the grade on the exam in a bin. Everybody who got A's, everybody got B's, everybody got C's. And the vertical axis would be a count of the number of students. We're going to do the same thing here. Our vertical axis is going to be a count, and the horizontal axis is going to be the bin size, where it's going to be our changes in positions. Okay? So for that, it says, create a copy of dx. Why do I always create copies? Because I don't want to screw anything up in case I need to redo it. So create a copy of a dx and sort it smallest to largest. It's just going to make life a little easier for us. Then we're going to create a new column for the bins. when I did my example for myself, I found a bin size of 2 times 10 to the minus 7 worked well. You can play around with bin size if you want. Your bins need to span the entire range of your data. And then using the data analysis tab, we can create a histogram. We can input the information for our data and our bins in the window that opens. And then the histogram data will form on a new tab, and then we can create a bar chart of it. Okay, so here we go. First part of that was to take G and create a copy of it. In case you haven't noticed, I like spaces in my Excel workbooks. Okay. And then it said, grab that data. Right, and sort it. So I'm going to come up to custom sort, tell it has a header, tell it it's that. And now you can see I start small and go big. And now I'm going to create a frame that says bin size. And I said I liked 2 times 10. 2 times 10 to the negative 7. And now I'm going to create a column for my bins. Okay. So my bins have to span my entire data. So my first bin needs to start at negative 0.0001. That's my first number up here. The next one is going to equal this number plus this one, but I'm going to want to drag this down. So I want to make sure that I put my dollar signs in to fix that cell. Right? So now when I drag this down, if I look, everywhere it goes, it's keeping J3 the same. Okay, so now I can do this all the way down until I get, you see I'm still negative. Okay, hold on guys. We're going to try this again. Let's just delete that. Okay. I did this a little bit differently when I did it for myself. So now you get to watch me play a little bit. The problem is 0.0001 is so much bigger than our bin size that adding our bin, which we need when we get closer to the center, it's taking too long. So what I want to do is I'm going to start at a more reasonable number, hopefully. And just make this work. So let's start at, say, -5e -5, and then do our bins from there and see if that works better. So this one plus that. You know what I did? I forgot the dollar signs. Look at that. Okay, are we getting anywhere quicker this time? Maybe. Yes. Okay, so our end on the positive side is at essentially 1 times 10 to the minus 4 again. So we need to extend further on the positive side. This is a little ridiculous, guys. Okay. Oh, so we've gone from -5 times 10 to the -5, and let's end at the same spot here. So we're going to get rid of a couple of these so that we go to 5 times 10 to the -5. It's not going to hurt things too much here. Okay. Sorry about that. Okay, so now we go over to the Data tab, Data Analysis, Insert Histogram. Hit OK. Now the input range. Input range are your DXs, so you want all of these. Okay, your bin range are your bins. So I'm going to start here and work my way up. Okay. I didn't click on anything else. I do notice that it says new worksheet apply, and I'm just going to hit OK because that tells me where it's going to open. Okay, and now you can see I have a new sheet at the bottom. I'm going to rename it so that you guys have it for you, called histogram, right? And as predicted, it gives us what are our bins and what are the frequencies. At this point, we can graph this, make a bar graph. Okay, so we're going to select data. We're going to hit add. Series name, not worried about it. The values of the series, this would be your y-axis, are going to be your bin frequencies. Okay, don't worry about the fact that there's 10 outside. It's not going to be a problem. Okay, the other thing you want to do is edit your horizontal axis, and that's going to be your bins. Okay. And so now you can see you have something that looks like a histogram with a central peak and then all of these outliers that are much bigger than that central peak. And the reason they're much bigger than that central peak is because those are the big jumps that were taken when tracking the data. Those aren't data. Those are big jumps to move from point to point. They're not representative of the actual motion of the particles. Therefore, we want to remove them. So what we're going to do is we're going to come over here and again make a copy of our DX. And this time we're going to look at our histogram and we're going to say, where are the big jumps? Where do they start? Or in other words, where does the central part of the histogram end? Well, it looks like here I go from, say, -6.8 times 10 to the -6 is one edge, and a comparable spot on the other side. I'm actually going to delete anything that's bigger on either side than 5 times 10 to the -6. So we come back over here, and we're going to delete anything that is outside of 5 times 10 to the -6 because that is a big jump. Oh, I went too far there, didn't I? 3, 3, 4. Aha, there's my break. So I'm going to delete those. And then I'm going to go to the other edge and do the exact same thing. Okay, so that would be all of these. I missed one. I know I missed one. Come back. Okay. Now for ease, what I'm going to do is I'm going to grab all of these. There they are. And I can grab onto them and I can just move them up so that they're not halfway down. Okay. This column, column M, represents the data for your or from your video. At this point, you can take this data and analyze it in exactly the same manner that you analyzed the Brownian Motion 1 data from the simulation. The parameters are all the same. So the sphere radius is still 0.5 microns. The viscosity is 0.001 Pascal seconds, I think was the correct answer. Temperature is 293. Time step is 5 seconds. Everything is the same. You just have to redo the analysis at this point. Okay? So what do you need to do? Right? Okay, so step 8. I actually did part of step 8 here for you. Look at the histogram. Anything outside that central peak is not your data. Okay, so then you copy dx and remove the points that were outside the central peak. What remains is your data set. Okay, so step 9 is to analyze the following the procedure in Brownian Motion 1, analyze the data, and answer the questions in Brownian Motion 3. If you don't remember how the simulation worked in Brownian Motion 1, remember you can always go back to it. Hopefully you have a copy of that data file, and if not, I hope you have a friend that can give it to you. Email me if you have questions. I would like this lab turned in by Friday, which will be April 3rd by midnight. That gives you a week to complete the lab. By midnight, remember, for Sakai is 11:55 p.m. So don't put it off to the last minute, please, guys. Okay, good luck.